Thanks, Leslie, for fighting through that introduction. I want to say it's an honor to be here today to talk to ASCE. One of the interesting things I think about ASCE is that they have a wide variety of programs. I've listened to people talk about policy and their experiences as an engineer. Philip's going to help me out there. And one of the things that you just have a wide variety, and you also manage to work in the technical side every now and then. If you remember when you were watching the Olympics a couple of weeks ago, when you had a judged event, you got style points and you got technical points. Well, I'm not saying we're not going to get any style points today, but we're going to go heavily on for the technical points. So I'm working with Leslie to see if you can get double PDH credits for that, if you can hang with me. We're going to talk about the Dallas Stormwater Pump Station program that we've been working on for the last several years. We've been doing this under the Trinity Watershed Management Group. It's a division of the City of Dallas. They're separate now. They're separate from Public Works and Water Utilities, and they really have four main missions. One of those is flood control. They operate the levees and the pump stations that we're going to talk about. They also do floodplain and drainage management for the storm sewer pipes and things like that. They have a stormwater component. If you live in the City of Dallas and you pay that stormwater fee, these are the guys that manage that. And then they also manage the big Trinity River Corridor project that this kind of all centers around. So it's a very dedicated group and it has a wide mission. One of the key features of this whole project and program is the Dallas floodway system itself. This is an incredible, I call it engineering feat, kind of the reason Dallas is here today. You probably couldn't build it today, but it's the reason we're here in a lot of ways. And back in the 20s, what happened was there were some floods that cut off downtown Dallas from Oak Cliff. And the city leaders decided they couldn't let that happen anymore, so they came up with a plan to build the Dallas floodway. And basically what it does is it diverts the Trinity River from the Elm Fork and the West Fork down through these two parallel lines that you see on the picture there. Those are levees that funnel the floodwaters through downtown and Oak Cliff. And then so on the top side is downtown. We estimate that it protects almost $8 billion in real estate from flooding. And then on the bottom side, the west levee side, is Oak Cliff, and there's thousands of homes in that area that are protected. The floodway system, like I said, it was devised and built in the 20s. The levees were built then. The system includes 30 miles of levees. The area is a lot larger than Central Park in New York. It has detention basins that store the floodwaters, gate structures, and then a series of 6 pump stations. Some of the stations actually are complexes with dual pump stations at each location, and all of that comes together to form the interior drainage or the floodway system. This is a little bit kind of a schematic of that. So you have the white area in the middle. That's where the levees are that funnel the floodwaters through. So when water from a storm drains from downtown towards the levees, it needs to get pumped over the levees, very similar to what happens in New Orleans and Sacramento and other cities all around the country. So it's a very unique system for Dallas for this area. And then those red dots on the top side and the bottom side are those 6 pump station locations. On the top side, downtown, we have Abel, Baker, and Hampton. On the bottom side, the Oak Cliff side, Charlie, Pavaho, and Delta. And so that makes up the system that protects all of that area from flooding. I want to say a little bit about the interior drainage system. It's incredible that guys back in the 20s using the tools that they used could come up with this. They got it right. This thing, they couldn't have envisioned that all of North Texas would develop like it has, all the way up to almost the Oklahoma border over to Fort Worth, and it still functions and carries a very large storm today. When I showed this picture to my wife, she said, "What is that yellow ruler-looking thing in the picture?" And I said, well, that's my high school slide rule from when I was in the slide rule club. Engineers, if you're my age, don't admit to your wife that you're in the slide rule club. Maybe you call it the non-digital computer club, but not the slide rule club. And I don't think those guys even had mechanical pencils back then. That little grinder thing, you had to put the pencil in there and do this. If you're a little bit younger than me, you probably don't know what I'm talking about doing this, but that's the tools they had to work with. And really the point that we need to make here is that This is a 100-year-old asset that was built back when we had this kind of stuff to work with. And really what we're doing today with the program that's going on and what the city of Dallas is accomplishing is really taking this asset into the next century and getting it ready for its next 100 years. When I was in London with my wife last November, there's a monument along the Thames River to the engineer that had a lot to do with the London drainage system. I think we need a monument like this to the engineers that designed the floodway system. And I won't make any comment about taking drainage monument pictures while I'm on vacation. So what got this started was the city, one of the councilmen several years ago realized that the pump stations and the levees and things might need to be upgraded. And so they put together some money in an effort to do a study to look at what needed to happen. And so we developed a program, we did a study, did all the hydrology and hydraulics, the flooding impacts, and came up with a plan to minimize the flooding and upgrade the system. What we tried to do is optimize the pumping capacity for what was there now and what needed to be built. Did all our hydrology and hydraulics and came up with a program, and then the city was able to get some money from the 2006 bond issue, which is one of the largest bond issues that the city has done, primarily related to drainage, to get the money to start on some of this. So our study came up with a lot of recommendations. Primarily, we realized that you've got a combination of storage and pumping that you can work with. The areas are so developed that you really can't get any more storage, so you need to build more pumping. And so at all of those locations that I mentioned earlier, something needed to be done. These are the recommendations for the new pump stations that we came up with. Currently, right now, Pavaho Station is built. Baker Station is under construction. And then soon, Able Pump Station, being designed by HDR, will be going under construction. So the total program cost was about $150 million. The city's not doing that all at once, but at least the 3 stations are online right now to get constructed. So once we got through with the study and the recommendations, we started working on the design for the 2 stations. And since this was envisioned to kind of set out the program for how it would be done later, we wanted to come up with design guidelines and things for the stations that would be built. This would really be the first upgrade of stations since the 1970s. One of the things we did was we came across this entity called a concrete volute pump that I'll talk about later that really kind of sets us apart from other stations. And some of the things that really brought this into the 21st century are some of these computational fluid dynamic modeling that we were able to do at each station and build physical models to make sure that when we put this all together and punch the button that it would work like we hoped it would. So back to the Dallas floodway system, what I'm really going to concentrate on today is just kind of a case study of the Pavaho station that it has been constructed. As I mentioned, there's others slated to be put online, and the Pavaho station is the one on the south side there, the west levee that protects a lot of area in Oak Cliff from flooding. It provides 100-year protection in the area that drains to it, and it impacts about 1,000 homes that were in the floodplain based on the study that we did. This is the current Pavaho pump station. We call it the Little House. It is about 2,000 square feet in size, 82,000 gallon per minute pumping capacity, built in the 50s, and it's really, we found out it was undersized, but it was doing its job for what it was. During the study, we looked at what areas were flooding in the Pavaho sump area, the area drained by the Pavaho pump station. And this is a plot of that floodplain. There's over 1,000 homes that were impacted in the floodplain. Those yellow and red dots kind of show which ones are impacted. So we ran our models and came up that if we had a certain size pump station, we could lower the flood elevation 2.5 feet, and we were only left with about 16 or 17 remaining homes in the floodplain. And those that are still there were just so low that it was, we determined it was economically infeasible to remove them for the incremental costs you would get in pumping. So the city's dealing with that. The station that we came up with ended up costing about $27 million. as I alluded to earlier, this is the first time that these concrete volute pumps were going to be used in the U.S. for pumping stormwater. Right now, they're used throughout the world in Europe and Asia, India, for pumping stormwater and also power plant cooling. So they're a good application for this. And what makes them really function well is that it's an integrated pump that is integrated into the station itself and the structure of the station. So we decided that Pavaho Station needed about 3 125,000 gallon per minute pumps to do its job. Those are with 2,200 horsepower motors, pretty large motors. And we found out that this concrete volute pump was going to work based on its technical merits. We also looked at other types of pumps to come up with this conclusion. Screw type pumps are pretty prevalent in New Orleans. We looked at those. Also, the current Dallas system is just all vertical turbine pumps, and I'll show you kind of how that works in a second. But we looked at those, and there's other types of vertical turbine pumps we looked at, but we settled on the concrete volute pump for these reasons. Really, it just made a lot of sense. When we're pumping over a levee, it's not like pumping into a long pipeline. You've got a low head, and you need a lot of water to get moved. So that's what these pumps do. The dynamic head is only about, at the max, 60 feet. It turns out that these pumps turn really slowly, probably a third as fast as some of the vertical turbines, so they're low maintenance, low vibration, got a high efficiency, so the city gets more out of their electrical dollar. And since the volute, or the bowl that the impeller turns around in, since that's concrete and it's a relatively high abrasion-resistant concrete, then these things last a long time. They're very durable. And I think one of the most important features that kind of helped us settle on this is that the concrete volute pump, and here's a cutaway of it, it's basically, all of that is part of the station. So you don't have a separate pump bell, you don't have separate components. You've got the impeller that turns inside the volute, and that's part of the concrete of the station. But this form suction inlet down at the bottom allows you to get really great hydraulic characteristics into the pump. So the impeller doesn't have to be submerged as much, and you don't have to have all that expensive concrete below it to get that submergence on the impellers, that net positive suction head. And so we estimated that saved the program about $10 million from being able to shallow up the station and really take advantage of these hydraulics. Just to kind of compare the two type pumps that we were dealing with, these vertical turbines are what are in the system now. And it's the one on the right with the green tube. Basically, that's just a straw that sticks down in a wet well and sucks up the water. And so you get vortexing, cavitation. They spin fast. So the city of Dallas actually has to take these out of service every 5 years and work them over so they can be ready for the next 5 years. That's expensive. They've got a lot of pumps they have to do this with. The concrete volute pumps, because of their slow turning speed, you don't need to pull them out but about every 20 years. And so further, confirmation that we were headed in the right direction. So this is a shot of the station under construction. Those are the suction bells being poured and formed. Kudos to our structural engineers for all the rebar that had to be put in there. It's not going anywhere. But one of the interesting things about how you cast these pumps into the part of the station, some manufacturers will build forms that they send out to the site, and basically you put the forms in place, put the rebar in around the corners and all that, get it set up, and then just do a mass pour. And that's a little bit tricky because of the rebar angles and all the setup you have to do. But the company that won the bid for Pavaho and Baker, FlowServe is the company, they're actually in Irving, they came up with an idea to use precast components for all that. So they precast the shapes and the volute and all that tricky stuff in their precast components, ship it to the site, you put it together like a big Lego set, maybe more like Duplo, the big ones. Put that together, lock it down, line it up, And so that forms the innards of the pump, and then you just do a mass pour around that, and it's really pretty slick. A lot less intense on setup. So there's another shot of the volute precast components, and then on the right there is the suction bells coming up after the volutes have been poured. And so that's just all part of the station. That's the suction bell part after it was poured. You can kind of get an idea of the size of that for this station. That splitter wall piece of concrete in the middle is another integral part of how the hydraulics work out on all this and make it really pretty slick. And then this is a shot of the impeller that was in the factory before it was shipped on the right. The distance from the floor to that blue paint is about 8 feet, so it's very large. But these things, there's a crane inside the station that can lift these out if they need to be serviced. And then on the left there is a picture of the impeller in place and what you see from the top. Of course, on a station like this, you've got your basic motors and gear drives and things to make the pump turn. In this case, all of this is electric. There's dual feeds to the station, no diesel backup or anything like that. The city's really got a good track record of having their electric system work on this, so we went with that. And then also, because the pumps turn so slowly, the motors that you get on the market turn a lot faster than that, so had to have gear reducers to reduce that speed down to the right turning speed for the pump. And then this is a shot of the finished pump floor area. It's about 10,000 square feet, almost 5 times bigger than Old Pavaho Station, and this is the finished part of it. The pumps are down below this floor. One of the things you'll notice if you drive out by the station are these weird-looking industrial Art Deco, whatever you want to call them, tubes, and they're actually functional. There's a purpose for them. When we started working on this, it was in about 07, 08, and there was a big bullseye on levees and levee systems caused by what happened in New Orleans for Hurricane Katrina. The Corps of Engineers really didn't want us to touch the levees to try to get these new pump stations to discharge over into the river. So we had a little bit of an issue there. I think we could have accomplished it at the time, but we were lucky enough that since the Old Pavaho Station was there, we just used the discharge pipes that already penetrated the levee, and that was our discharge for the pump station. But what we needed to do was, since you couldn't go up and over the levee at the time, we needed to hydraulically separate the river from the pump station in the area that it protected. So those tubes are higher than the levees, and water cannot physically back up into the pump station. There's no valves, there's no mechanical elements there. It's just a big dumb system that sits there and works, and nobody has to operate it unless they need to. So those protect the system. One of the things, though, that we realized early is that when you have something this big and you've got water crashing down like that over the inverted tube and down into a header, your basic Mannings and Q equal VA just doesn't work. There's a lot of air that gets entrained in these pipes as that water's crashing around. So we had to handle that in the design. This is kind of a 3D rendering of that discharge system that we came up with. There's the inverted U-tubes. We call them the candy canes. So when that water crashes down from the top of the U-tube and then crashes down into that 96-inch discharge header, all kinds of air is getting entrained into the system. So we came up with these air vents on the top to dissipate some of that, and then we ended up having to put a big air vent at the end right before it goes out into the levee to get rid of all that air and make the hydraulics work and make sure we got the flow that we needed out of the station. So we did a lot of computational fluid dynamic models to do this, and then we also built a 1:10 scale physical model of that whole setup in the lab, and then ran water through it, looked at the air that it was getting entrained, and figured out how to get rid of that to make it all work. And so we came up with the air stack and the 96-inch air stack, and really that was kind of a blessing, it turned out, because the contractor was able to use that piece of pipe poking up to create a test loop inside the sump to test the pumps to make sure they were going to get the capacity that we needed. This is a shot of the model that was built. It's kind of hard to see sometimes because the pipe that was used was clear plastic, so you could see what was going on. But the inverted U-tubes on the left, the discharge in the center, and then you kind of see the scale of the model. I've got some videos of that if anybody wants to see it after the presentation. I don't know that we have time for that here, but pretty interesting geeky type videos of water flowing. So the station was substantially complete in August 2012, and then we had the opening ceremony in September of 2012. But right after it was finished, we got about a 3-inch rain, and it worked. So everything was good. It pumped water. Everybody could sleep that night. I just want to say a word about me being up here. I'm not up here alone. Just was fortunate enough to be able to tell you about this great project. These are the people that we worked with at the City of Dallas, the Trinity Watershed Management Group. And then we had a whole host of engineers that helped us out, program managers, sub-consultants, engineers, technicians that really made this come together. A lot of smart people put this together and made it work. With that, I'll turn it over to Leslie.
All right, I think we have time for a few questions.
Yes, sir. Well, I think in Texas it's volute, but in Europe they say volute. It's the pump bowl, I guess, the part that the impeller spins around. I'd heard it before. I've gotten very familiar with it lately, but yeah, that's the term. Yes, sir. I think they probably, I'm trying to remember, he asked, the question was, are the concrete volute pumps cheaper than the vertical turbines? I think they're probably a little more expensive just because of, kind of the setup. But in the end, when we considered operational costs and how it affected the cost of the station itself for the structural part, it all came together to be cheaper. The pumps, in this case, I think each one was about $2.5 million for the pump itself. Patrick? Yeah, the question is how much we might have saved for not having valves on those big inverted U-tubes. Oh, I would say, in the $500,000 range easily with 72-inch, valves times 3. It was pretty expensive. We did probably spend a little bit in structural cost to get those tubes to stay upright, but I think having a simple system. The City of Dallas likes things simple. They don't like to maintain things and have things that have to be oiled and greased and all that. So this is a good. They like this idea. Yeah, the question is the time frame for the rest of the pump program. Really, it's kind of unclear at this time. The city, I think, wants to continue to do that. They're looking for ways to get money to start design, and there's really not. I don't believe there's money for construction yet, but I know that they're committed to getting this finished. So it might stretch out a little more than originally thought, but I feel confident they'll end up doing it. So it could be another 5 or so years probably for the whole thing. Oh, yes, sir. Yeah, question about the discharge pipe that we used, the existing set of pipes through the levee. We were able to see that pretty well, and it was in great shape. And it's a pipe that was already set up to be pressurized because of the current pump station that was pumping through it, and we did the hydraulics, and everything looked like it was going to work. So, and that's another reason for having the inverted U's. Once it gets to the top of the U, it can just gravity flow out, and so it makes the hydraulics a little bit better. So, I think we, in a way, we got lucky having that there, but it worked out and was able to keep the program moving because we didn't have some of the issues with the core on how we would tie into the levee. Yes, in the back there. Right, yeah. The question, I guess, is about gravity flow when you've got low flow in the river and you've got a high head on the protected side and getting that water through. Yeah, there's a gravity flow ability. We've got sluice gates and flap gates. So all that can be opened up and let the gravity flow take place. Turns out that the city, gates can get stuck, all that kind of stuff. So they kind of like to operate in a pumping mode a lot of the time, and that just is kind of the way they operate the system. But it's got a gravity flow component to it. Yes, sir. Right. Yeah, the question was about the Trinity Parkway. That's the big freeway that's going to go on the downtown side of the levees and carry that flow from 35 up to the tollway or wherever. So that parkway is going to have another levee to the side of the levee that'll be the surface for the parkway. And so these stations right now, they discharge right on the other side of the levee. So they're going to have to increase the length of the discharge pipes when all that comes in. In fact, on Able Station, that station is right down by where the new lake is going to be built for the Trinity project. It's about a 30-acre lake, I think. So those pipes are going to have to go under the lake out to where the river is going to be when all that's finished. So they're going to have to increase the length of those by thousands of feet probably to make that happen. But that's all predicated on when the other projects come in. But right now they're made to function with what's there. Scott. Yeah, a question about any other modeling improvements in the sump. On Baker Station, we've got a condition where we've got most of the flow coming into the sump on one side, and it's got to drop down about 20 feet, 15 feet to get into the sump. So we did a physical model of a drop structure on that and made sure that worked. There's also a lot of pretty weird hydraulics going on in the Baker sump with where the old stations are and how all that works. I know that some of the guys around here told me they might have worked on some of those projects. We did have to model that, and we did CFD modeling and physical modeling on all that and changed it up. Okay, thank you.